All right, let's get the show. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. Important reminders, we have a test starting tomorrow. There's still the practice test up. At this point, I think about only 3 people have taken the practice test. So the rest of you should try to get on that as soon as possible so you can ask questions. The plan today, so there are two, I guess there are 3 sections, but there are 2 main topics that we have left to cover. So one is going to be volumes of revolution. The other one is going to be surface areas of revolution. So what I want to do is today I want to cover volumes of revolution, and tomorrow I would cover surface areas of revolution. So the plan, hopefully, is that I would spend the first 2 hours, I didn't get here, spend the first 2 hours of class and finish volumes with that, and leave the last hour for questions that anyone might have regarding the test tomorrow or anything that you've been studying. And tomorrow, I should actually be able to cover areas in even less time. So maybe the first hour of class, and then we'd have 2 hours left over to play with. And then you can ask me more questions, which could probably even include things going up to the final. So the final will be sort of like a combination of test 1 and test 2 with the stuff that's left off of test 2. So, which is like what we've been covering Monday through today, or yesterday through today.
Sorry, I had a
Yes.
question.
Mhm.
So I noticed on the notes page on the OneNote, you have 20 lectures up. Do we have a lecture on Monday or?
No.
Okay.
Yeah.
Okay.
So I just created a bunch of pages. I didn't really like count specifically how many lectures there
Okay.
were.
No,
So I just created them ahead of time to like conserve space and in case I wanted to pre-type notes. So yeah. So
right,
tomorrow is going to be our last lecture, and it won't be the full class even. And the plan is for today not to be the full class because I want to take questions later. But that being said, let's actually jump into it. Yeah. Maxim's got the natural lighting today, so all right, it's gonna be a good day. All right, so quick recap of what we did yesterday. We sketched more polar curves, which is also something that you need to know for the test. So you have to be able to sketch the trig curve first, and then using the trig curve, be able to sketch the polar curve, what it would look like. And we kind of went through the steps on that. Then we looked at sketching conic sections. So the only thing I needed you to know from this section is how to sketch ellipses and hyperbolas, and just know the components of doing that. So what would the A be, what the B would be, how to construct the rectangle, how to draw an ellipse based on that, and how to identify the vertices after doing that. Also, you need to know how to do the same thing with hyperbolas. So how to construct that rectangle, knowing that the asymptotes come from extending the diagonals, and knowing whether your curve should open side to side, east to west, or north to south, up and down, based on the form of the equation. So we did a couple examples of that, and we saw that the only thing that can be a slight hiccup here is that you have to do a little bit of algebra to get it into the right form. But once it's in the right form, hopefully we saw that sketching wasn't going to be that bad. So we did a few examples of that. This we skipped, you can completely ignore. It's just that sometimes like ellipses or hyperbolas are tilted and it's harder to do things, calculations with them. So there's a whole method of like rotating the axes to make it. Essentially, you're actually creating a different coordinate system based on rotation, and that will help you deal with it easier. But you can completely ignore that. I'm not going to test you on it or anything, but I left it there just in case anyone's curious. Then we went to the calculus with polar coordinates. Remember, polar coordinates are essentially defined by these parametric equations. So we can find the derivative using the appropriate formulas. We could also find where tangent lines are vertical or horizontal. find slope. We could also find arc length using the arc length formula, but that reduces if you simplified everything into this bottom formula right here. And yeah, we use that. We then looked at finding areas in polar coordinates. So we have the general formula for that. And we did some examples of that. So these are like applications of integral, this and arc length. And what we're going to be doing today and tomorrow are also further applications of integrals. So we're actually using integrals to do certain things. So in this case, it was to find the area enclosed inside of polar curves in various scenarios. And that's where we kind of ended. Today, we want to do volumes, which is we're going to cover what we left off in chapter 5. So if you went back to the syllabus, there's that. We're covering chapter topic 15. We've actually covered this already, covered that yesterday. Now we're going to today finish up topic 15, and then tomorrow finish up topic 17. Yes, we have class tomorrow. And exam 2 opens at 3 p.m. tomorrow. Okay, so it opens at 3 p.m. It's due at 9 p.m. the following day. And the practice for test 2 closes at 3 p.m. No, wait, actually, I think I close it at 2 p.m. I did something at 2 p.m. I think the practice test closes at 3 p.m., but I have the answers set to show themselves at 2 p.m. But I would recommend you not look at the answers before actually practicing it on your own. So yeah, today we're going to talk about volumes. So we're going to do more on volumes and area. Well, area we're going to do tomorrow. But today we're going to talk about volume, using integrals to find volume. And when you go to Calc 3, you're going to find better methods of doing this. So, and this will be obsolete, but for Calc 2, we're gonna do this. So one of those topics that, yeah, it might be obsolete, but it's actually pretty fun. When you get into it. So it'll be nice to do something a little bit fun. The overarching concept is the idea of finding volumes of solid objects using the cross-sectional area. So the idea here being that if I have, let's say, so there's some object and it's 3D, you know, and there's some object here that I'm trying to measure the volume, right? And let's suppose, for the sake of argument, that I have a function a of x that tells me the area of this face, right? So every time I slice at a certain x value, there's a function that tells me what is the area of that face at that x value. So this is the area of the green part. Okay. Now what we can do is we can slice this thing up into many infinitesimal slices. Very small, very thin slices, each with a length of delta x. And then the idea is here that the volume is going to just be the sum of the ax times delta x, because we know from high school geometry that the volume of a prism, which is what we're finding here, all these slices, we can think of them as a prism, is just one closed curve elongated for some length. And so it's the area, the volume of such an object is the area of the base times the height. You know, that's why the volume of a cylinder is pi r squared times h, and so on. Why the volume of a box is the length times width times the height, because we know this for prisms. So the volume is just going to be taking the area of the base multiplied by the height, which in this time is delta x. And of course, this will just be an approximation, but the actual volume is going to be equal to, of course, the limit of this. And you might recognize that as a Riemann sum. So that becomes your dx, this becomes your a of x, and the summation, the limit of the summation becomes the integral. And so we have this formula taking effect, right? So this is just assuming we can find a function that describes the area of one face of a solid object. We can actually find the volume of that object, right? So that's just a conceptual thing to know, how we can apply integration to finding volume in this context. But what we are going to do is we're going to actually look at some very specific, or one very specific scenario in which this is true. And these are going to be volumes of rotation. So this is when we get a solid object by rotating a region around some axis, right? So that leads us to volumes of revolution. And so the idea here, a solid object is formed by rotating a region about some axis, and we want to find its volume. So the idea is, I have some region in the plane, could be whatever, right? Let's call that region R, right? So R is this region. And what I do is, let's say, just for the sake of argument, I'm going to rotate this region about the x-axis, right? So that leads to something that looks like this, right? So you can imagine the x-axis is coming out of the page. Looks like a ham, right? So if you were to take one slice of this thing, that way you'll see the region R embedded in it. But now we're rotating it around the axes. And this kind of creates a solid object for us, right? Now it turns out, of course, that this, because you're rotating, you're actually going to form a circle. And so what you have is, from the axis, which is the center, you can measure here, which is going to be R equals R of x equals the radius. So this, in this case, would be like your f of x, you know, so probably shouldn't call it R, but whatever. Like the big R here is, I'm talking about the radius. And what we can do then is we can actually figure out that the area function here is going to be pi times the radius squared. I don't want to mix up these R's. Let's call this E. E is the region. I call it R later on, but at that point, hopefully, it's not going to be make anything confusing. Okay. So then we have that this is the cross-sectional area. So this means that we can find volume of this object of revolution via, we just integrate the a of x, which is what the previous formula said. But in this case, that's going to be pi times r squared. Okay, so that's the idea. And we can go from, say, here A to B. So we can integrate from A to B. Okay, so that's just me applying this idea to a general concept of forming an object through revolution. And this is called a volume of revolution. Okay. Now, this particular instance leads us to the formula. That's what's known as the disk method. Okay. And the idea behind the disk method is because you get a disk here. And we know the area of the disk is going to be pi r squared. And so that leads us to this formula, which I just derived. Now, there's a slightly different version of this formula, which is more general, called the washer method, where you take a big R squared minus a little r squared. And the big R is going to be the outer radius and the little r is going to be the inner radius. And the idea behind that is, sometimes your object can have a gap in it. So let's say your object looks like this, and you're rotating it around here. That is going to create, an object that's rotating around here. But then when you look from the sideways, the outer curve is going to create something, a ring, but the inner curve also creates something. So that means your cross section looks like a washer. Now, I don't know if anyone knows what a washer is. That's that little plastic thingy that you put on a pipe to prevent leaking at the joints. I don't know. So there's this, a thin plate with a hole in it is called a washer, right? So you kind of create an object like that. And so what you can do is you can find the volume that you would get from the inner part and subtract the volume of the whole thing. And you can find the volume of the piece with the hole drilled into it. And so that's what leads you to a formula like this. But either way, it's the same concept. It's just that one, there's a gap in it, and the other one there isn't. So like in this case, there was no gap here. There's no inner radius to worry about. But if this was cut out open here, then there would be an inner radius to worry about. But they're essentially the same thing. So we're using either the first one or the last one. And they're really coming from the same concept. It's just that sometimes there might be two curves to worry about, and the presence of another curve creates a gap. So that is the disk method. And that is pretty much it. That's the formula. So now what I'm going to do is I'm going to teach you how to apply the formula. What should you think about when applying this formula, and just how to solve a problem using this method and using this formula. So some things to talk about. General concept, we're going to talk about things like radii and height, like radiuses, where we're talking about here, radii. And one thing you need to remember is that these are distances. And so you should remember that distances, they're measured in a specific way. So if it's a horizontal distance, we can measure it by taking the right minus the left. You can think of like a number line, right? So if you want to find the distance between, say, 3 and 5, this distance here it's 5 minus 3, which is 2, right? And this is like right minus left. So that's the concept I'm talking about here. So if you're measuring a horizontal distance, you do right minus left. If you're measuring a vertical distance, you would do top minus bottom, right? So a very basic concept, but sometimes in the minutia of everything, students forget the simplest concepts. So I just want to actually write it down and tell you, oh, if you're measuring a horizontal length, take the thing on the right, subtract the thing on the left. If you're measuring a vertical length, take the thing on the top, subtract the thing on the bottom. Okay, so that's important. Another thing that's going to be useful is that the D in disk, you can think of this as meaning different, D for different, disk method, different, and different in the sense that if we're rotating about a line that has the form y equals k, then your integral is going to be with respect to x. So the y and the x, these are different variables. So, and by the way, the x-axis is the line y equals 0. So the x-axis counts as a y line, right? The x-axis is y equals 0, right? So this is included in this, right? So if you're going around a horizontal line, your function should be in terms of x because you are measuring like the height. So say I have this line over here and I'm rotating about this, then my radius would be measuring vertically. And so there's some function f of x or height that can tell me about it. So I can think of things in terms of x's if I'm going around a y equals something kind of line. This also includes the x-axis, right? Now, if I'm going about an x equals something kind of line, things kind of change. So this is, you know, here's a line I'm going around, you know, like x equals 5 or whatever. Then my radius would be measured horizontally. And this means like my function would look something like this, which is x is a function of y. Right? So based on the line you're going around, if you look at the equation of that line, whatever variable is used to describe that line, it's only going to be a horizontal or vertical one. We're not going to rotate around slant lines. Either going to be a vertical or horizontal line. Your integral should be set up in the opposite variable of the equation of the line. And so that's what I mean by disk means different. Okay. And knowing what variable to set things up is it's actually going to be very important. And we're going to get to that pretty soon. But that is, those are the main concepts. Now, I said a lot. Let's actually jump in and actually do something. We're going to do these examples here. And we're going to do a bunch here. So let's do this first one. So you can see from start to finish how this would work. Okay. So here's a straightforward direct problem. Find the volume of a solid obtained by rotating the region bounded by y equals radical x and y equals 0 for x between 0 and 4 about the x-axis. So I'm rotating this region about the x-axis, right? So let's actually look at the region. Sketching is often going to be very useful. I should put that sketching is very useful here. It's a general tip. Now, luckily for us, the kind of things that you'd have to sketch for a problem like this, they're not going to be anything crazy difficult. They should be things that you can sketch relatively easy. Like radical x is something you should know by heart. Right? So the region is going to look like, you know, from here, radical x. But we're going from 0 to 4. So this is my region here. So this is my region R. And we are told we are rotating about the x-axis. Right? So I'm going to obtain an object like this, right? Which is called a solid paraboloid, right? Okay. You don't need this second graph. This is the important graph. The one in the plane is going to be the important graph. Okay. So what you can do now is we're going to use volume equals pi times integral of r squared dx. I know it's dx because we're going about the x-axis, which is y equals 0. So because I'm going around a y line, I know I have to set up everything in with respect to x. So my radius is going to be this it's going to be given by the height of this function, which is y equals the square root of x. And so this r that I'm talking about here is actually for radius. So here I want to integrate from 0 to 4. My radius is radical x. Why is it radical x? Well, notice that the bottom of the region is the line y equals 0. The top of the region is y equals radical x. What is the distance needing to measure here? Top minus bottom. It's going to be radical x minus 0, right? Where the radius is a distance. So you're measuring a vertical distance. You want to go top minus bottom. The top of the region minus the bottom of the region, or the outer curve minus the inner curve. Okay, so here the radius is going to be radical x minus 0 times dx squared, and we're going from 0 to 4. And we're pretty much done. So from here on out, we're just evaluating the integral. So it's x squared over 2 between 0 and 4 times pi. That'll be 8 pi. Right, so that's this problem here. So the sketching and the integral itself shouldn't be crazy. Like, you've done way crazier integrals in test 1. What's important here is going to be the concept of how to set up the integral. Okay, so now questions. Kind of understand what I did? So I have that formula, volume equals pi r squared, integral of that. R is just the radius. The variable I set it up in is the opposite variable of the equation of the line I'm rotating about. And so now I just go in and I measure the distances. The radius is a vertical distance, so I take the top curve minus the bottom curve, and I write it with respect to x's. After that, it's just doing the integral, which at this point, it should be a relatively simple integral compared to like what you've been seeing. Okay, no one's stopping me, so I'm gonna move on. All right, so here, this problem, I just want you to set up the integral. That's going to do this. Okay. So we're going to set up the integral that is going to compute this volume of revolution. Okay. So again, we're going to look at what region we're describing here. So there's a region bounded by x squared and 4, y equals x squared and y equals 4. I want to take that region and I want to rotate it around the x-axis. This is going to create a solid object, and I want to find the volume of that object, right? The volume of this rotation, or the volume of this revolution. Not revolution like give us free, revolution like revolving around. Okay, so we're going to, again, sketch. It's always very useful. So here we have our y equals x squared. Then we'd have a horizontal line, y equals 4. And I care about the region bounded between them. So that blue region, what am I going to do with that blue region? I will rotate it around the x-axis. So I'm writing that little curl there just to remind myself of what axis I'm rotating around. Now, I want you to notice here that this is going to create a washer type situation. Because notice that this curve here is going to rotate and give me a circle, and this one out here is going to rotate and give me a circle. So at this point, I'm getting a washer. So this one requires the general formula. Notice that there's going to be one radius to measure to this lower curve. And then there's going to be another radius to measure to the other end of R. Now this one is called little r, or the inner radius. And the longer one is called big R, or the outer radius. And the formula to find the volume in such a case using the washer method is just pi times the integral of big R squared minus little r squared. Now I'm going around the x-axis. The equation of the x-axis is y equals 0. For the disk method, d means different. I'm going to use the opposite variable. So the line is y equals 0. I am going to use with respect to x. So here, big R is just 4, technically 4 minus 0. Little r is going to be x squared. Right. Technically, it's 4 minus 0, 4 minus 0, because I'm going around. This is going about y equals 0. So I want the distance between y equals 0. So on this level, y equals 0. I want the distance between 4 and y equals 0, and I want the distance between x squared and y equals 0. So that's my big R and little r. And so therefore the volume is going to be given by pi times the integral of big R squared minus the little r squared. Now, what are the limits? Well, we need to actually figure out the bounds for this. Right, so. And you kind of just set those equal to each other. So you said x squared equals 4. This means x equals plus or minus 2. So it's going to be a minus 2 plus 2. And so those are going to be the limits here. So this will be the answer. Questions? Comments, concerns? Do you understand why I had to use the big R and little r versus just the big R?
Is there a more precise mathematical way to determine when the little r is required? Like if it's difficult to graph?
The more precise way would probably be to do calculations with these curves. So first you'd have to figure out the intersection. So you know that your x's are ranging between -2 and 2. And then you'd have to figure out which curve is farther away, right? Now, when your y equals 0, meaning like it's actually the x-axis, then your little r is obviously 0 units away, and then the little r disappears, and you get the first one. But if your y is something else, then that means that there's going to be another thing to worry about. And so to find the big R, you want to find the larger difference. So you have to see, okay, for x between -2 and 2, which one would give me the bigger number? So I plug in, say, x equals 1, right? That's a number between -2 and 2. The difference between 1 and 4 is 3. The difference between 1 and x squared would be 1, right? So the y equals 4 is clearly giving me the bigger difference, right? So it comes down to like first figuring out the intersections, and you can test values inside the intersections to see who is giving you the biggest difference. But I like doing that. One, I think it's more computationally destructive, and too computationally heavy, and two, you can have a situation that looks like this, right? So this is like your F and your G. So if you tested just a point here, your F is going to be the little r and your G is going to be the big R. But if you happen to test over here, you're going to realize that, oh, the actually now they kind of, so the R is the G. In this case, the big R would be the G. This would be little r because it's closer. And then the big R would be here. So the thing is, you run some risks that you're plugging in. One, you have to make sure that you're plugging in the right values. And two, in general, it would be hard to know if you're like, if something switches places and you have to figure it out. And we're actually going to see examples where this is the case, where things will switch places. And the quickest way to figure that out is to just do the sketch. So technically, you could figure things out by plugging in values and checking the difference, but I don't think it's worth it. I think in general, it's going to be much easier, much quicker, and much safer to just quickly sketch the graphs. Like, you're not going to be asked to sketch anything crazy here. So
Okay,
yeah,
thank you.
so manually checking the difference by plugging in test points between all the curves present would be the way you can figure it out.
Actually, wait, a random thought just popped into my head about that.
Yeah.
Could you use like a definite integral to see which is closer to the x-axis at all times?
Sure, but that would be equivalent to just doing them separately, right? If you do them separately as an integral, and you'd be able to figure out, oh, this one here gave me the bigger value. That must have been the big R, right? Like, you'd find it out after the fact, and then you subtract them. So you can do like the method with this curve, and then do the method separately with this curve, and you would notice that this one would give you the bigger answer, and so you just know the answer is to take this and subtract that. So that's a like reverse engineering way kind of doing it. But you know, again, that way would be more computationally lighter, and you'd essentially be doing the same amount of work. But I feel like it's psychologically it's going to be different. There's kind of a back and forth that's going on. Also, you don't really know how these functions would interplay with each other. Like, sometimes you might have something over here that might cancel something over there, and the integrals together are easier to deal with than separately. So yeah, so it's not like this is the only way to do it, but like doing it in one formula, doing a sketch, figuring out the big R and the little r is the most efficient and safest way to do it in my experience. So like, I don't like any other way. Like, there'll be times where it'll work out nicely, but there's so much that can go wrong. Like, I don't want to, like, I wouldn't risk it. I think in terms of setup, this is pretty straightforward, and I leave it there. We also have a question in the okay, so someone's asking about the homework. So the homework would be, they would give you maybe slightly more complicated functions here, but on the homework would assume that, oh, you can use a calculator to crunch the numbers or something like that. Like, the things that I would give you by hand won't be as big. But if you're interested in particular homework problems, like, I am leaving time at the end of class today, so we can go over that later. But for now, the kind of things that I would ask you on a test wouldn't be something with some crazy numbers, as well as if I'm teaching you something for the first time, I don't want to teach you with crazy numbers. I actually just want to keep things simple so that you get the concept. because the concept is the most important thing. Like once you get the concept down, the actual numbers won't matter. Like if I change this to an 8, like it doesn't change anything, right? You just move an 8 and put, like once you know how to deal with it with a simple number, you'll know how to deal with it with a more complicated number. You're essentially doing the same thing with different numbers. So yeah, the homework might give you like slightly more complicated functions, but you can use a calculator to crunch the numbers there if it makes it easier for you. But conceptually, it shouldn't be any different. Okay. So here in this example, we're going to set up a bunch, but they're all going to be set up on the same region. So we're going to do just one sketch, figure out everything about that sketch. But I just want you to see some variety on the axes we can go around and what to do in each case. All right. So here I'm going to set them up, but you guys might want to evaluate these integrals on your own time. I think I wrote down all the answers for them. So I'll tell you what the answers are, and you guys should, you know, it's practice. It's practice doing some integrals. You should do the practice. But here the main thing is to set up. So we're going to always do the same region. R, big R, is the region that's bounded by y equals x squared and y equals 3x. And we want to set up integrals to find the volume obtained by rotating R around these 6 different kinds of axes. And we're going to be setting up the integrals to actually do that. And you can kind of see the differences in how each integral will be set up and what kind of calculations you'd have to do, what variable you'd have to set it up in, etc. Okay. So let's actually do that. So R is bounded by y equals x squared and y equals 3x. So let's do the one around the x-axis. So I quickly sketch these because again, that's the safest thing to do. Y equals x squared, y equals 3x. So I see that this is the guy we want. Of course, I can figure out what these intersections are. So let's figure out that. It's kind of obvious that they would both meet at 0, but for intersections, you can just set them equal to each other. X squared equals 3x. This will mean that x squared minus 3x equals 0. Factor out a common x. So you get x equals 0 or x equals 3. So this would be 3, that would be 0. Now, of course, when x equals 3, you know that your y equals 3 squared, which is 9. And so that allows me to fill in here. And you'll see later why we want to know the 9. It's because you might not want to know it in every situation, but there are going to be situations where we have to do things in terms of y. So I'm just finding it ahead of time. So this is going to be our picture. And I want to rotate around the x-axis. So I'm going to draw that little thing to remind myself I'm rotating this around the x-axis. So now what I'm going to do is there's going to be a radius measuring to the closer function and a radius measuring to the farther function. That's your big R, this is your little r. What is big R? Well, big R is measuring to the line, and that's going to be 3x. Your little r is measuring into the quadratic, so that's going to be x squared. And that's it. Now I can plug into the formula. I know it's dx because I'm going around y equals 0. That's the axis I'm rotating around. So I know everything is in terms of x's, and that's why I just put the x's here. So this would just be pi. Now, because everything is in terms of x, my limits come from the x-axis. So this is 0 and 3. Big R squared minus little r squared. And that would be the integral setup. Which, FYI, that is equal to 162 pi over 5. If you actually were to work that out. So you should try that on your own, and you should get 162 pi over 5 when you do that integral. Any questions? Okay, let's do the other one. So again, here, it's going to be the same diagram, so I'm just going to copy it. So I know this here is at 9. That's at 3. That's at 0. This is y equals 3x. This is y equals x squared. Now this time I am going around the y-axis. So my radius is measured with the y-axis as the center, which means there's going to be that measuring to the first curve, and then there's another one measuring to the second curve. So this is my little r, this is my big R. Now, we're going around the axis is x equals 0. So what you should recognize is that this is a dy integral. Disk different, right? You're doing the disk method, it's different, right? So you're going around x equals something, all your variables should be in terms of y's. So when you're measuring this horizontal distance here, it's going to be measured as a function of y. So you actually would want to change all these guys to be functions of y. So we have y equals x squared. This would mean that your x is equal to plus or minus rad y. The positive y is applicable here. And if your y is equal to 3x, this means that your x is equal to y over 3. And notice here, your little r measures to the y over 3, and your big R measures to the radical. So here, and since I'm integrating with respect to y, my limits come from the numbers on the y. So that's the 0 and the 9. So that's the integral. By the way, if you do that, that'll be 27 pi over 2. So you can have the same region, but based on where I'm telling you to rotate it about, you can get a different volume, right? And you might have to set it up in a different variable. And it's up to you to know which one of these variables you want to set things up into, right? So this tells you that you want to actually write things out in everything should be in terms of y. Why? Because you're going around a line x equals 0. And we have that concept, D means different. You're going around x equals 0, you do dy. You're going around y equals something, you do dx. So that would be the setup for this one. Questions? Right, let's do an interesting one. Here, we're not going around an axis. We're going to go around the line x equals 4. Once again, it's the same picture, so I'm just going to copy it. So y equals 3x, y equals x squared. So y-axis, that's the x-axis. This is the region. I know this intersection happens at 3. And this one happens at 9. Now, what I'm doing is now, in this case, I'm rotating around a different line. There's a line here, x equals 4. And that's the line I'm rotating around. Which means I have my outer radius measuring to here, and my inner radius measuring to here. And furthermore, we're going about x equals something. So this means we should be doing things dy. So we're thinking of these in terms of the y's. So this one I would think of in terms of y, x is the square root of y, because we're on the positive side here. And this I would think of as x equals y over 3. So I'm not looking at the functions as functions of x. I'm looking at them as functions of y. Okay, now, participation. Let's see who's paying attention. What would big R and little r be in this scenario?
Is it 4 minus x squared and 4 minus 3x?
Almost. We have to do in terms of y's, right? But yes, it's 4 minus. Y, you're measuring a horizontal distance. This guy here is on the right. And your functions are on the left. How do you measure a horizontal distance? Right minus left. So the right is x equals 4. So it's right, because that's, x equals 4 is the right. Now the left is going to be the curve x equals y over 3. So your x equals y over 3 is on the left. So you are measuring a horizontal distance, right minus left. So it's going to be 4 minus the function for big R, and it's going to be 4 minus the other function for little r. So it's going to be 4 minus the line for big R. It's going to be 4 minus the parabola for little r, which in this case, it becomes a radical because we're writing in terms of y. So this would be 4 minus rad y. Now, once you have that, the rest is easy. You just have that formula. It's pi times the integral of big R squared minus little r squared. This case is from 0 to 9 because we're taking our limits from the y's. And I think I did this one as well. This is 45 pi over 2. We actually did that computation. So we're slowly adding concepts. So our first example didn't have a little r. All our other examples had little r's, but the second example didn't have this axis being 0 automatically, but it does show up. So right here, when I'm writing this minus 0, that's what I was still doing here. I was doing like right minus left. Well, in this case, it was top minus bottom. Just be careful. If you're going around the x-axis or the y-axis, then that counts for 0. And so you wouldn't really see it. And yeah. So we have that. Let's do it again. Let's go over x equals minus 1. Once again, it's the same region. I don't want you to worry about graphing anything right now. So it's the same region. So that, boom. And we have that, boom. So y equals x squared, y equals 3x. This is the region here. This intersection is going to be 3. It's going to be 9. Now this time, I'm going around a line over here. Not drawn to scale, obviously. This is x equals minus 1. And I want to go around that. Let me put that world somewhere else. So now, from the axis, you measure it to the function, to the outline of the shaded region. So one distance is measuring to the inner function, which is the line, that's your little r. The other one is measuring to the parabola, which is the big R. Right? And you'll notice here, based on where you are, the little r and big R can switch from the parabola to the line. Now, if you're in a situation where you're plugging in numbers and guessing and checking, like to be able to switch on a pivot like this, it's going to be hard. You're going to it's much easier to just draw it and you can see, oh, that's on the left, that's on the right. This one is farther from the axis than that one, right? The picture, it's just, it'll talk to you, right? Besides, you want to get used to drawing the pictures because in Calc 3, a similar thing is going to be true very often. Like in 3D, to actually try to set up a problem, you're really going to want to know what things look like. And you don't really want to be stuck plugging in a bunch of numbers into a function with 2 inputs or 3 inputs or 4 inputs. And it's much easier to just know, oh, this surface looks like this, so it has to be on top of this one. And so that would be the farther one. And so I can set things up this way. It's much more efficient to just do a quick sketch. Now, similarly here, big R, little r. First thing I notice is that I'm going around x equals something, which means everything should be in terms of y. This is dy since going about x equals -1. So the x, I have to switch here. So now I want to find what is the big R. That is going to be, again, right minus left. In this case, the parabola is on the right, which I'm looking at as the radical of y. The left would be x equals -1. So this is right minus left. So it's radical y plus 1. Then for little r, it's the straight line minus the -1. So this is going to be y over 3 minus -1. So it's y over 3 plus 1, right minus left. In this case, the axis is always on the left. So the x equals -1 is to the left of the shaded region. So to figure out the distance to the axis, you're going to subtract the axis from the thing that you're measuring to. Horizontal distance, right minus left. So those are your big R's and little R's. You already know the intersections, so now you're done. Well, you're done if all you had to do was set up the integral. But if I ask you to compute the integral, you'd have to work a little bit more. So big R squared minus little r squared. And we actually, I did this one. It actually coincidentally gave the same answer as the last one, 45 pi over 2. So there's that one. So we'll take a little break here. When we come back, we'll do the last two, and then we'll talk about another method of volumes of revolution. But yeah, so during the break, you can take a drink of water, but check the notes. Make sure you kind of see how I'm setting these things up so you can ask questions. But we will go on to y equals 10, rotating the same region. So the picture is going to look the same except for the axis of rotation, and we'll figure out how to do that one. So take 5 minutes here, and I'll see you guys in a little bit. All right, let's finish up the last two. Y equals 10. All right, so once again, same region. So all right, so now we're rotating around this line. Y equals 10. So now I need to measure my radii. So that goes to the outer curve. That's big R. This goes to the inner curve. That's little r. Because I'm going around y equals 10, I know I'm doing a dx integral. And so I'm measuring everything in terms of x's. So y equals a function of x. And so my big R and little r, these are going to be top minus bottom because I'm measuring a vertical distance. So the top is y equals 10. It's above everything. So top is always going to be 10. Now for the big R, it goes from 10 to the parabola. And for the little r, it goes from 10 to the line. So those are my radii. Then I can just plug in. From 0 to 3, because I'm using the x limits. Big R squared minus little r squared. That's my integral. And this actually works out to 288 pi over 5. Questions? And of course, to evaluate this integral, you just expand the parentheses. It's just power rule all around. So it's power rule everywhere. And I think that's been the case with pretty much everything. Yeah, this is all power rule. So the actual integration isn't bad. And the curves isn't bad. It's just seeing, do you know this formula? Do you know how to choose the pieces in the formula? Do you know how to find the big R? Do you know how to find the little r and plug them in? After that, the integration should be on almost autopilot. It's going to be a lot easier than the integration we did on test 1, generally speaking. So let's do the last one. Once again, it's the same region. And copy the graph. Y equals x squared. Y equals 3x. That's the shaded region. Now y equals -2. So there's a line down here. Just going to draw that in. Call that y equals -2. And I know I want to rotate around that line. Which means that's where I'm measuring my radii from. That is the outer radius because it measures to the farther curve. That is the inner radius because it measures to the closer curve. And once again, now I can set up my r's. It's going to be top minus bottom. And I also know, because I'm going about y equals something, the integral is dx. So all my functions are going to be in terms of x. My limits are going to be in terms of x. Everything's going to be in terms of x. And so top minus bottom. So for big R, the top is 3x, the bottom is -2. So it's 3x minus a -2. So it's 3x plus 2. Little r, it's going to be the parabola minus the -2. Those are my radii. So that means the volume is pi times the integral of big R squared minus little r squared. The limits go on the x-axis. And if we're doing this, I think this would be 252 pi over 5. Any questions on that? So that was the disk washer method. And the idea comes from the fact when you rotate it around, you get like a washer type shape for the cross-sectional area of the solid that you form. Turns out that's not the only way to think about things though. And so there's actually another method for finding volume. And that's what we're going to talk about now. That's actually in the next section. So everything we've done so far is in section 5.2 of the text. Now we're going to go into 5.3, which shows us another method for finding volume. It's called the shell method, or the method of cylindrical shells. Okay. And so here's the idea. So again, let's say we have a region that we want to rotate it about some axis. Let's say I'm rotating it about the y-axis in this demonstration. So here's the thing that we do. We kind of take this Riemann sums kind of approach, and we dissect this thing up into a bunch of rectangular thingies. So I go in and I'm like slicing this up, right, in terms of these little rectangles. Right, so say there's one rectangle here, right? But I'm slicing these up in a bunch of rectangles. Okay. Very thin rectangles that fills up the whole shape. So there comes a point. Now what we do is we take a radius measuring to one of these entire rectangles, right? So we're moving this entire piece here, rotating around. Now that creates something like this. It creates a cylindrical shell, right? Notice that it'll look like the casing of a cylinder. And you, by the way, you do this with all intermediate ones as well. So you have like shells inside of shells inside of shells. And so that's how you add up all these shells. Now for any one of these shells, like you pick this outer one right here, you can unravel it, right? So you can unravel this shell. Now, if I make the thickness of each shell like delta X, then we actually know the dimensions of all of these guys. So I can call this, let's say I call this the height of the shell. Call that H, which in this case can just be measured by f of x or whatever function we're using, right? It turns out that this distance here is, because it's a circle, so the length of that is going to be the circumference. This is going to be 2 pi r, right? Where r is just going to be the radius here. And then the thickness here, that's delta x. And you can do this for each individual shell, each individual casing. So you kind of slice thing up and you rotate one piece at a time. Each piece would look like some individual shell casing, a cylindrical shell casing. And they kind of, like a bunch of Russian dolls, they kind of form this solid. Right? One shell inside of another, inside of another, inside of another. They form this solid of revolution. Now, if you start looking at the volume of this thing, it's going to be 2 pi RH times delta x. And of course, you're adding this up among all the shells. Right? You're doing this for each shell. So with a finite number of shells, it's only an approximation, but of course, you let the limit as the number of shells go off to infinity of this guy. And lo and behold, you get a Riemann sum that gives you this integral of 2 pi RH dx. Where here, R is going to be the radius and H is going to be the height of each shell. Right, so that leads to this general formula. You don't need to know how to derive it, you just need to know the formula. So it's the integral of 2 pi RH. R is the radius, H is the height. Now, there is a the word is slipping my mind, just like a cork idiosyncrasy of this thing. So in this setup, we always, so our X is going to go between A and B, right? But for a generic shell, we think of that as being at position X, where your X is ranging between A and B. But the shell itself is always position X, or in the opposite case, it would be in position Y, right? But that's how you want to think of this. So you're always measuring to a distance, you're measuring the radius to a position X, right? And it's always just X, literally X, right? So it's not going to be a part of the function or anything like that. The radius has nothing to do with the function itself, technically. It just has to do with some position X that's within the shaded region. And that's how the radius is going to be measured. But again, radius is a distance. So in this case, it's going to be a horizontal distance. It'll be X minus whatever the axis is. The height of the shell, now that is where the function comes in, because how tall this guy is depending on the function. It goes from the x-axis up to as tall as the function is. So the height would depend on the function that's involved. So in the R and the H in this scenario, you measure them in particular ways. So let's talk about the concepts and actually using this formula. The first thing is that in the shell method, you can think of the S as standing for the same, in the sense that, unlike with the disk method, where disk would stand for different, shell means the same, if you're going around y equals something, you do the integral with respect to y, the same. It follows the variable of the rotating axis, right? If you're going around x equals something, you do dx. All right, so that's a distinction between this method. So you use the same variable as the equation of the axis that you're rotating around. With the disk method, it was the opposite. Okay, so that's important to know. So that's an important concept. So that's the first one. The second concept is the radius. It has a specific form. And essentially it's going to be the following, right? It's always going to be like x minus the axis or the axis minus x, because you're always thinking of the shell as being at position x. And so if x is on the right and the axis of rotation is on the left, it's going to be x minus the axis. If x is on the left and the axis of rotation is on the right, that is going to be the axis minus x, right? And so on. And in the vertical case, a very similar thing is going to be true. So the shell is actually always at position X or position Y, depending on the variable that you're going to use. So let's actually do some illustrations here. All right, so look at this scenario. So in this case, whenever you're rotating around something, your axis is going to be one thing over here. Your shell is going to be a part in your shaded region that's parallel to that axis. Now, what your job is to measure the distance to this shell. That's your R. Now, what that is, this, because you're rotating around, this line is x equals 0. So this shell would be at position X. And so your R in this case is going to be x minus 0, essentially. So here it's just going to be x minus 0. So your R is just x. The height is the height of the shell. Now, in my illustration here, there are two functions. There's a function f of x on top, function g of x on the bottom. So this is simply going to be, it's a vertical distance, so it's top minus bottom. And that would be how you find your RH in general. Okay, so let's do that again. Let's say here, I'm going around an axis x equals 2. Because I'm going around x equals something, everything is dx. So this shell is at position x. I want to measure the radius is the distance moving to that shell. The radius is a horizontal distance. You always measure horizontal distances with right minus left. Here, x is on the right, minus 2 is on the left. So the radius is going to be x minus a minus 2. Now, the height of the shell is the vertical height of the green thing. Vertical distances is top minus bottom. The top is f of x, the bottom is g of x. So notice here, the radius is horizontal. This is right minus left. The height is vertical. This is top minus bottom. So you're actually measuring you're measuring both a horizontal and a vertical distance for this method, right? But again, if you just remember right minus left and top minus bottom, it's not going to be too complicated. You're just going to plug it in. So instead of like an inner radius and an outer radius, there is no such thing in the shell method. It's you have to find a radius and a height always. You have to find both of these things. So get another example. Here I'm rotating around the x-axis, which means I'm measuring a distance to there. Because this is the line y equals 0, the shell is at position y. So the radius is going to be y minus 0 because it's top minus bottom. And the bottom here is y equals 0. Now, obviously, the height is this horizontal length here. So this is going to be right minus left. What is on the right? According to the graph here, my function of y, k of y is on the right. My function h of y is on the left. I shouldn't have used h. Let's use j. So that's how you'd find the radius and the height. Similarly here, call this j. Once again, I'm going around y equals something. So my shell is at position y. The radius is measuring to this distance. So I'm going from y equals 3 to y. So this, in this setup, this is the top, this is the bottom. So the radius is going to be top minus bottom. The height is going to be right minus left because it's measuring this horizontal green distance. So that's going to be k of y minus j of y. And so that's how you do the setups for the shell method. Okay, so quickly want to check if you get how to do this. So these are some for you guys to try. So here, tell me what the radius would look like for all of these examples. Class participation, chime in. This first one right here. What would the radius be? Anyone? You are. Any guesses? Oh, I have a guess in the chat here. X minus 5. Where would the X be? Where is your X location? Remember, the X location is in the shaded region, right? There's going to be a shell here that's parallel to the axis. That is in position X. And your radius is measuring that distance here. It's 5 minus X, so it's the opposite. It's always right minus left. The 5 is on the right, the X is on the left. The X is always with the shaded region. Okay, let's try again. This one. Tell me what R is. Right, 2 minus X. Because over here is position X. We're measuring a horizontal distance from this to that. 2 is on the right, X is on the left. Cool. Let's jump down here. What is R? Almost wrong variable. It's Y plus 1 because you're going around Y equals something, right? Remember, the shell method takes the same variable as the axis of rotation. So this is a Y line. So that means your shell here is parallel to that, but that is at position Y. And you're measuring a vertical distance. So you're measuring Y minus a minus 1, you get Y plus 1. Here. Radius. Yep, X plus 5. I mean, you wrote it as minus a minus 5, which means you're thinking about it the correct way, right? So the shell is here, parallel to the axis of rotation. You're measuring a distance over here. Now, because this is X equals something, this is at position X. So there's X on the left, minus 5 on the right, X minus a minus 5. Okay. Quicker, what's the radius here? Anyone? Come on, grasshoppers, you got it. It's the wax on, wax off. Let's get this.
Ten minus y.
10 minus y, right? And you said at the same time, someone put it in the chat. So horizontal shell here, parallel to the axis of rotation. That is going to be at position y. I know it's at position y because the equation of the line is that y equals something. And then I want to measure this radius. So it's top minus bottom. 10 is on top, y is on the bottom. 10 minus y. Here, it's going to be a similar thing. Shell is over here. That's at position y. Minus 3 is on top. So this is actually going to be minus 3 minus y. And don't worry, if you're trying to worry like, whoa, that looks negative. It looks negative, but it's not, because obviously here your y has to be smaller than minus 3. So your y could be like minus 5 is an example of a number. Take minus 3 minus a minus 5, you get a positive number, right? So don't let how the actual form of the thing look fool you. You do top minus bottom, you will not be wrong, right? That's how we measure it. Go by the concept, not by, you know, so I don't want anyone to set up a radius like this and like, whoa, dude, that must be wrong. Like, no, that's the right radius. Okay, remember those concepts, right? Vertical distance is top minus bottom. I don't know what's going on with the internet here. Okay. Vertical distance is top minus bottom. Horizontal distance is right minus left. Always. Doesn't matter what the thingies look like that you're subtracting. Doesn't matter if they both have negative signs on them or one has negative sign and it looks like a completely negative thing. No. If you do right minus left or top minus bottom, you will always get a positive number, regardless of how it might look in symbols. Okay. So here, this is actually exactly the same example that we did in parts for the disk method, but now we're going to do it for the shell method. So all the integrals here will have the same answers corresponding to the integrals above, but now I'm just using a different method to do them. So we're just going to do the shell method. So it's the same thingy, but we're doing shell. So let's actually just go through and set these up. So first, let's look at doing this thing over the x-axis. So we had y equals x squared. We had y equals 3x. We knew that this was 3. That was 9. So this is the region we care about. This is 0. And we are going around the x-axis. But now we're doing the shell method, not the disk method. So again, the shell is going to be some vertical thing here, and we're measuring to that. That is your R. Now the height is going to be, maybe I should do that in a different color. What can I do? Height is going to be that horizontal distance, like the length of the shell, the green shell. Right, so you fill in a shell that's parallel to the axis of rotation. Okay, now the axis of rotation is the x-axis. This is the line y equals 0. This means the shell is at position y. So this tells you that your R is going to be top minus bottom, y minus the axis. What is your H going to be? Well, H is a horizontal distance. That's going to be right minus left. Now remember, your H has to be in terms of y's because we're going around. Y equals something. The shell method says S stands for same, right? The S in shell, same. So whatever axis you're going around, you need the same variable. So we're going around y equals something. You need all your functions to be in terms of y's. So your H, the right side is the parabola, which in terms of y is radical y. The left side is the straight line, which in terms of y is going to be y over 3. So in this case, we know our volume equals 2 pi times the integral of RH dy. So in this case, our volume is going to be 2 pi times the integral from 0 to 9, because those are the numbers on the y-axis, of R, which is y, times h. And so that would be the setup here. Which, by the way, this is equal to, it'll actually be the same as the part A and the other one. Yeah, so this one, when we're doing the disk method, it looks like it's an integral with respect to x. For the shell method, it was the opposite, integral with respect to y, but it's the same answer, 162 pi over 5. So that would stay x-axis. Let's do it again. So now we're going to do the same problem going around the y-axis. So once again, going to sketch the function. Now it's y equals x squared, y equals 3x. We're going around here. Now, the y-axis, this is the equation x equals 0, which means this is a dx integral. Everything should be in terms of x's because we're doing the shell method. Now, we go in, we create our shell. One example will do, right? So there's something parallel to the axis of rotation. We want to measure the distance to that. That's your r. And the height of that thing is the h. So in this case, pink is very thick. Just a lot of pink, very overbearing pink, overwhelmingly pink. So let's actually just make that a little bit clearer. So the they say that pink makes you aggressive. Like if you like paint a room in pink, like it tends to. I don't know if that's true. I've heard someone say that though. I don't remember if it was a reputable source. But like, you do your math homework in pink. It's like you're very angry by the end of it. Okay, so the r is a horizontal distance, which by the way, we're going around x equals something. So this is at position x. And of course, the y-axis is x equals 0. So your r is going to be x minus 0. Your h is going to be top minus bottom. Now the top is the line, the bottom is the parabola. So now we can get this into the formula. Volume is 2 pi times the integral of r times h. And this is in terms of x, so that's 0 to 3. And that would be the integral that you would need to compute to find the volume. This is actually exactly the same as the previous question. So the one for here, so 27 pi over 2. Any questions on that? Okay. Moving on. Going on x equals 4. Same region. I don't want to waste any brain power on that. So y equals x squared. Y equals 3x. And we're going to run here, x equals 4. So go in, create our shell. Parallel to the axis of rotation, we're measuring to that guy is our r, and our height is the height of that guy. So r is going to be a left minus a right minus a left. The position here is x because this is x equals 4. So the radius is going to be 4 minus x, which is right minus left. The height is going to be top minus bottom, which is going to be the line minus the parabola. So this means that your volume is 2 pi times the integral of r times h from 0 to 3. If we were to compute that, we're in part C, you'd get 45 pi over 2. Details left to the reader. So see, relatively speaking, like setting up these integrals shouldn't be the hard part. The hard part would be if you have to like, and I mean, hard part here really just means, oh, it'll take a while for me to write it down. And it's hard in terms of endurance, kind of. Like the integral itself is not going to be that bad. You expand the parentheses, it's a bunch of power rules. And then you go through the motions and integrate and plug that in. X equals -1. Same sort of deal. Y equals x squared. Y equals 3x. And this time we're going around x equals -1. What's going on with this guy? It's not stopping me from doing it, but it'll that means it's not syncing with the website properly. Maybe it's the website that's having an issue. Anyway, so again, shell is here, parallel to the axis of rotation. It's x equals something, so this is at position x. So there's a height that I have to worry about. There's also a radius I have to worry about. However, we don't have to worry too much because the radius is going to be right minus left. And the height is going to be top minus bottom. It's 2 pi r times h. That is the integral that will give us the volume of rotation of this object. That was the answer for D. (45 pi over 2). So that would be that setup. Let's do it again. Like we're going to be doing it so much. You're gonna be dreaming about this tonight. You'll be able to do it in your sleep. Oh, I have to find the shell. Wake up in a cold sweat. Top minus bottom, right minus left, right minus left. Oh my god, I gotta find the radius. The radius is coming. So same region. Y equals x squared. Y equals 3x. Here we're going around y equals 10. So there's a line across here. Y equals 10. That means for shell, we're doing everything dy. Everything needs to be a function of y. We go in here. We locate our shell. Just take any random shell in the middle of the shaded region. We want to measure the distance from the axis to that shell. That's called r. We want to measure the length of that shell. That's called h. R is going to be top minus bottom. The shell is at position Y. So that's just going to be 10 is above that. So it's 10 minus Y. The height is going to be right minus left. So it's going to be the parabola minus the line, but the parabola in terms of Y is radical Y, and the line is Y over 3. So this means your volume is 2 pi times the integral of r times h. Zero to 9 because we're doing it in terms of y, and 0 and 9 are the limits on the y-axis. If you do that integral, you get the same thing as e from the previous example. 288 pi over 5. So that's that one. So see, getting to the setup shouldn't be too hard. So if I ask you about, I can describe a region to you and just say, hey, set up an integral to find the volume. And showing your work would be, again, just like I do in class. Like showing your work to me means you're writing things down exactly how I would write them down in class. So I would expect to see a sketch. I'd expect to see you tell me what the r and the h is. And I would expect to see you set up the correct integral after that. And then if there are a bunch of options, you would select that option or select none of these, apply, and upload your work if required. But this is it. As you can see, like once you get into a groove with these things, you do quite a few of these problems. It's not going to be, it's a lot easier than what we're doing on test 1 stuff. Test 1 was the harder part of the class. Let's do. It's not the last example because there is something else I want to actually talk about, but try to get through the rest relatively quickly. So here. Y equals x squared. Y equals 3x. Okay, so here we're going on y equals -2. That tells me that I'm doing everything dy. Go in here, find my shell, parallel to the axis of rotation, I need to measure R, which is the distance to the shell. I need to also measure H, which is the height of the shell. This is a dy integral, so this is at position Y. Notice that it is on top of Y equals -2. So my R is Y minus a -2. H is going to be a horizontal length. It's right minus left. It's the parabola minus the line. In terms of Y, the parabola is radical Y and the line is that. So this means our volume is 2 pi times the integral of R times H dy 0 to 9. That would be the setup. If you're required to evaluate the integral, the answer you should get is 252 pi over 5. Right? So hopefully you get that. Now, one thing I need to deal with is at this point, you might be thinking, like, why do we need these two methods, Jhevon? Are you just wanting to give us stuff to confuse us? Like, we learned the dis method, was happy with the dis method. Some of you might even like the shell method better. Like, man, the shell method is better. Like, I'm going to always use that. Forget the dis method, right? But so here's the thing. It turns out that there are scenarios in which one might be better than the other. So in these problems, the examples that I gave you so far, I specified which method I want you to use. It turns out that I could just ask you to find a volume of revolution, but I don't specify the method, and you would have to think about which method is best to apply. Now, it turns out that that is a thing to worry about. Like, theoretically speaking, you can apply either method to something, but there are many cases in which one is better than the other. In the sense that it would be easier to calculate, it would be less work to calculate, all of that. So that's what I want to talk about now. So we learned two methods, how to choose the right one. Now, to illustrate a situation where that choice might matter, I came up with an example. So let's consider this region. Where it is bounded by y equals x squared and y equals 2 minus x. So here's the picture of this region. So, I mean, I'm not going to show you how to find the intersection, but you can. This is going to be -2, and this is going to be 1. Okay, so that's the region. Now, here's what I want to do. I want you to rotate this around. Technically, if draw the scale, the line should be after the intersection. Rotate this around the line x equals 4. Now, consider doing the above via the disk method. And then I'm going to want you to consider doing the above via the shell method. So I'm going to copy these so I can mark up this diagram and you can see. And so you can visually see why one method might be better than the other, which again is another reason why you might want to just sketch a picture, because it's not always ahead of time you're going to know which method you should be applying, so you know which differences you should be checking, right? Consider doing the above via the shell method. And then there's going to be another example here. We'll get to that later. Okay. So now here's something I want you to notice. It turns out that, and I don't know if you'll notice this at a glance. Yeah, that's okay, Kevin. I don't notice if you'll notice this at a glance, but if you're to do the disk method, you are going to run into some issues here. Not issues in terms of, oh, the problem is going to be impossible to solve with the disk method, but you would essentially be doubling your work if you choose the disk method. Now, why would that be the case? Well, notice that something very strange happens around this intersection point. Right? Just imagine the world above that intersection point and the world below that intersection point. Why would that intersection point matter? Well, let's see. For the disk method, we need to measure the inner and the outer radius, right? So let's say I'm above this pink broken line. What is the outer radius? Well, it is going to be, boom, all the way to the parabola. What is the inner radius? All the way to the line. Okay, all right, what's the problem? Well, what about below that dotted line? Well, notice, so here, I would tell you that those two are actually different. So below that pink line, the outer radius is, yeah, it's still the parabola. But look at what the inner radius is. The inner radius no longer goes to the straight line. There is a second inner radius, right? Which means you actually need two integrals to actually do this. You need one integral for above this intersection where you have the R1 and the, so here, notice that we need dos integrals. You would need a volume equals pi times integral of R1 squared minus R2 squared above the pink line. And then you need to add that to the integral of R2 squared minus little r2 squared. Well, this should be R1 squared. Below the pink line, right? Because when I measure my inner and outer radiuses, radii, they actually change. The inner radius switched on me. There was a point where the inner radius was the straight line, but then there came a point where the inner radius is the parabola. That's an issue. Like that, the basis of this method is setting things up based on the inner and outer radiuses. Every time I get a new set of radii, I need to do a whole new integral. So I would need to find the volume for rotating the top part, then find the volume for rotating the bottom part with two separate integrals and then add them together. Ain't nobody got time for that, right? However, look at the same thing with the shell method. Same region, rotating around the same thing. What do I need for the shell method to work? Well, I need to go into the shaded region, create a shell. Cool. What is the radius? There's only one radius to worry about. Oh, I ran into my own hand just now. The distance to that shell. What else do I need to find the shell method? I need to find the height of this. Do either of these change? No, R is always just going to be the same generic term for the shell. It's just at position X, right? Does the height change? Well, no, no matter where the shell is, the top is the line, the bottom is the parabola. The top is the line, the bottom is parabola all the time, the whole time. It never switches on me. Nothing switches. There's only one R and one H. So here, you only need one integral. So if I were to give you this this kind of scenario, and I were to tell you, oh, find the volume of revolution of this region R rotated about X equals 4. It turns out one method is better than the other. Like you should be able to look at this picture, or you should be able to draw this picture and then observe that the disk method is an inefficient method for this, whereas the shell method would work. And by the way, it's not that the disk method is the one that would mess up, because if I went around a horizontal line, the opposite will be true. My shell would have different heights below and above, but the disk method would only have one inner radius and one outer radius. So depending on which line I'm going about, I can actually change which method would be more efficient, right? So it's not that, oh, why are you teaching us two methods? You just make it, no, like one method can be better than the other one, right? And it's up to you to figure out which is which. So you might, so it's good to know both, because depending on the scenario, you might have to choose one versus the other, and you might have to know what is required to set up one versus what is required to set up the other one, and does anything switch on me, right? So I was talking about an example earlier about the function switching like this, and this is a scenario. It doesn't look nearly as complicated. It's a problem in a straight line. We've been doing this, like, we did this like 14 times already. We did 14 examples with a problem in a straight line, and we never had this consideration. But tilt the straight line up a little bit, and you're in a very different scenario, right? So here, for the above, shell method is better. Okay, so it's not just a matter of, oh, I'll just learn one of them and forget the other one. You should need to know both of them, because there are times when one is not, one is better than the other. So, and that's what, so this is the last example. That's what this example is meant to convey. So you have a problem like this. And I could ask you either one of these. Chances are in a single problem, I wouldn't ask you to do the thing twice. Or I would ask you which method is better for each of these, blah, blah, blah. I could ask something like that. And that's just like one answer. But I want you to appreciate what would actually be better in what situation here. So here, I just ask you to find, using a method of your choice, find the volume obtained by R when rotated about blah or blah. So the main thing I want you to do is to figure out which method is going to be better, if any. It could be the case where either one can work, like we did in examples before, and then apply the method, right? So let's look at this region, and let's actually look at it rotated around y equals 4 and see what would we want to do here. So let's look at this region. So where we want to plot this. So x equals y squared. That's just like a sideways parabola. And then you minus 3, so you shift to the left. So that guy looks like this. X equals y squared minus 3. So this will go down to minus 3. Okay, cool. Then we have x equals 2y, or you can think of this as y equals 1/2 x. Either way, it's a line of positive slope passing through the origin. So it's going to be a line like this. X equals 2y. And we want the region bounded between them. So it's going to be this. Okay, now need to find the intersections. That means you're going to set y squared minus 3 equals 2y. Y squared minus 2y minus 3 equals 0. That's 3 and 1. Minus 3 plus 1. So y equals 3 or y equals minus 1. So obviously this here is the minus 1. And this here is the 3. Now, of course, when y equals 3, your x would be 2 times 3, which is 6. So this point here corresponds to 6. And when y equals minus 1, your x is going to be 2 times minus 1 equals minus 2. So this is a minus 2. Okay, so that is our region. Now, I'm just going to copy this because I don't want to have to sketch it again. Okay, so that is the region. Now, in the first one, we want to rotate around y equals 4. So there's a line up here. Y equals 4, and I'm going around that. So, question, this method or a shell method is better? Throwing it out to the class. And don't just flip a coin. Actually, think about it for a little bit. Get this right. Okay, ideas? Like here I said, use a method of your choice. So you're going to pick a method and you're going to go in. So you want to make sure it's most efficient. Maybe it's a trick question. Maybe they're both just as good as the other. What do you guys think? Anyone who can answer in the next 10 seconds, I'll give 5 extra points on test 1. Go. Disk. Okay, so I only got one answer as direct message. Disk. Okay, so let's actually think about this. What would I need to get the disk method to work? So let's see if that is the correct guess. This method means I need to pick an inner and an outer radius. So let's say I'm over here, inner radius, parabola. Outer radius, line. Seems okay? Well, what if I'm over here? Inner radius, parabola. Outer radius, parabola. My big R actually changes depending on where I am. So this is no bueno, it's not this method. Shell is better. With the shell, I would need to create a horizontal thingy here. And no matter where I create this horizontal thingy, notice that on the right side of that horizontal thingy is going to be the straight line. And on the left side of that horizontal thingy is going to be the parabola. So the H does not change. That's my H. And then no matter where this thing is, that's just the R is going to be top minus bottom, and the position of the shell is always going to be Y. So it's always going to be 4 minus Y, no matter where the shell is. So moving the shell around isn't going to change what these guys are. So this is R. These are all going to be the same R. R is going to be 4 minus Y. Your H is going to be the line in terms of Y, which is 2Y, minus the parabola in terms of Y, because again, right minus left. The line is on the right, the parabola is on the left. So your H in this case is going to be 3 plus 2Y minus Y squared. And so you would set up the volume. 2 pi times the integral of R times H. And since we're looking at Y, we want the limits on the Y axis. So that's going to be from -1 up to 3. That's our guy. Now, if you were to, I don't remember if I actually wrote down the answer to this. I'll check my notes. Yeah, this one was actually computationally heavy. Like I wouldn't ask these numbers. It was 2,432 pi over 15. Yeah. So it gets annoying towards the end, because when you'd expand, you do the power rule, you'd get a bunch of fractions, and then you're plugging in the numbers. So to get the final answer, you're adding up a bunch of fractions. Kind of gets annoying, but at the very least, you should be able to set this up and identify which method was better. Here, the shell method was better. The disk method would require 2 integrals. If we look at this from the other perspective, going around x equals 8. So say here is the line x equals 8. So I might think, okay, I want to do the shell method, right? So you think about the shell method, right? Whichever method is your favorite method, you think about that first. It doesn't matter, just pick one. Because once you pick one, you should be able to set it up and know, is this really what I want to do? You ask yourself, do you really want to do that? Because here, notice what would happen if I put the shell here and I look at what my H needs to be. H is going between the parabola and the straight line. However, if I were to move my shell over here, now what is H doing? H is going between the parabola and the parabola. Of course, you'd write it in the other variable. So one would go through a positive radical, one would go to the negative radical, but the idea is the same. the bottom portion, the bottom is different, right? On one side, the bottom is the line. On the other side, the bottom would be the parabola. So if my first knee-jerk reaction would be, hey, shell method, I should within short order realize that, nah, that's not a good idea. And then I would backtrack and go to the other one. So yeah, shell would not be what we want to do here, because to get the shell to work, is going to require two integrals, because my height is going to change. The radius is always going to be the same, but the height is going to change. Conversely, if I said, all right, disk method, or someone, if you love the disk method, the first thing you thought about was the disk method, you should be able to identify that, okay, that would work. The outer radius and the inner radius is what you would need. So the outer radius is going to the parabola, and the inner radius is going to the line. And notice that no matter where you are, the inner radius is always the line. No matter where in the shaded region you go, that's always the line. And no matter where in the shaded region you go, the outer radius is always heading all the way to the parabola. So big R is always the same. It's going to be right minus left, where the left is the parabola, the right is x equals 8. And the little r is always going to be the same. So I was going to go from right to left, where the left is the line, the right is the 8. So in this scenario, the disk method is better. So we know what we would need to set up here. We need to find big R and little r. Now big R, and again, the disk method, we're going around x equals 8. So again, it's a dy integral, because d for different. So you're going around x equals something, you do in terms of y. Big R is going to be right minus left, which is 8 minus the parabola. And then the little r is going to be right minus left, which is 8 minus the line. So this would be 11 minus y squared. This would be 8 minus 2. I guess I didn't have to rewrite that. That's as simple as you can get here. So now the volume would be pi times big R squared minus little r squared. And it's the y again, so it's minus 1 to 3. And oh, I mixed these up. So this was the previous one was the answer for this. And this one should have been, I think, 64 pi. Because I had the same picture and I mixed up the thingies. Right. So you need to know both methods, because one can be more the better choice than the other. So yeah, so at this point, that's the topics. That's all we want to do today. So we went over a little bit, but for the remainder, I can take questions. So I would say, if you have any questions from the homework or from the, questions from the homework or from the practice problems in the syllabus, I'd probably take those first. If you want to ask me questions on the practice test, I would rather, if you didn't take the practice test, to actually leave at that point, and then just try the practice test on your own. But first, I'll take questions from other stuff, and then I'll take questions from the practice test, and at that point, anyone who didn't do the practice test can leave, because I don't want you to know the answers. You should actually try it yourself. And actually practice. So there were not many people, but a couple people had problems uploading on in Gradescope. That shouldn't have problems. So make sure you know how to upload in Gradescope. Make sure you know how to do it quickly and efficiently, and not through some complicated process. So a part of the practice test is for you to hash that out. Like if you run out of time uploading on the practice test, you're going to do it on the real test as well. So actually run through the test for real. Do your work, upload your answers, like do with the test run. So questions. Well, there was a question asked in the chat earlier, I think. So it's the volume solid road. Okay, so, and this is from the homework, right? That doesn't look like something I put on the practice test. Oh, I didn't put anything here on the practice test. So this topic isn't on the practice test. So this is like a Q&A. This is from homework. I don't know what problem, but it's some problem on the homework. So the region R was bounded by y equals x squared minus 14x plus 48 and y equals 0. Rotated about what? So for the first one, like y equals x squared, I can just set up the diagram at this point. X squared minus 14x plus 48. That is, I'll try to factor this. 48 is 8 times 6, right? And 8 plus 6 is 14. So here's 8 and 6, minus and minus. So you can get x equals 8 and x equals 6 are the intercepts. And so the picture would look like a parabola like that, where this goes between 6 and 8. And so this is your region here. Right? So you just do that and you'd figure out the picture. So that's the region. And then the question is rotating around the x-axis. Did it give you a specific method? Both methods should be fine here, but if it didn't give you a method, I would just do the disk method. That would be easier. So I'm just measuring that r, and I'm going to use volume equals pi r squared dx. So it's going around the x-axis. So I'm going around the line y equals 0, so I'm doing things in terms of dx. So it's going to be r is going to be top minus bottom. So I'm going to subtract this guy. X squared minus 14x plus 48. So your r is going to be 14x minus x squared minus 48. And so your volume would be pi times the integral between 6 and 8. And then you just calculate that. Shell method is doable, but it'll be a little bit annoying. Because you'd have to be able to write this as a function of y, which is doable, but it's going to be very annoying. So sometimes it's not that it'll double up on the integral, but sometimes it's like you can't write the function in the right variable very easily. So with the shell method, I'm going around y equals something. I'd have to write all the functions in terms of y. And so I'd have to like write this as x equals some function of y. You can do it using the quadratic formula, but it's not gonna be great. It's gonna have a bunch of radicals in it, minus b plus or minus square root of b squared minus 4ac. It's gonna be very annoying to do this with the shell method. So the disk method is actually better here. by quite a margin, I would say. What else? So that was that. Homework 3, Cartesian coordinates is 1, 1, find the polar coordinates. When your theta is between 0. Okay, so yeah, so this is an important problem type. I definitely ask questions like this. So let's actually get this one. So I have x comma y equals 1, 1, right in r comma theta with 2 requirements. R is positive and your theta is between 0 and 2 pi. And r is negative and your theta is between 0 and 2 pi. That looks like the question. Okay, so remember, we know that x squared plus y squared equals r squared. So this means 2 equals r squared. This means that your r is plus or minus rad 2. And we could plot this. Notice that this is the point 1, 1. And so we want our theta and our r. So to find the theta, I can do tan inverse of y over x. So that's just the tan inverse of 1, which is pi over 4. So I can move, so this would be an angle pi over 4. So one thing, r theta, I can do it as rad 2 pi over 4. Or, so I want the negative. So I want it possibly on the other side. So if this here is pi over 4, the reference angle going around all the way here would be pi over 4 plus pi. So that would be 5 pi over 4 and a negative r. So I can get minus rad 2 and 5 pi over 4. And those two would be equivalent. That was a homework problem. I feel like that's something I did in class. The numbers look familiar to me, but I don't remember. I don't remember exactly. No. So you only get a 10% bump on the homework if you make it to 90%. So if you can get up to 90% on the homework, I'll give you the last 10% for free. But it's not like I just add 10%. Like if you get like a 58% on the homework, you get 50%. But if you get like a 91% on the homework, I'll give you 100% for free. I'll go right up to 100 once you can hit the mark of 90. No, not 89, 90. Yeah, you have to hit the 90. So if you make it to 89, you try to do something to get that extra 1%. Because it'll be worth 11% to you.
And also the homework is due on Saturday, right?
I can double check. I thought so, but let me double check right now. Just give me a couple seconds. Homework is due on 8/6 at 2 a.m. So it's Saturday at 2 in the morning. I don't know why it set it to 2 in the morning, but that's what it is. Yeah. So just think of it as Saturday at midnight. Just think of it that way so you don't mess up. Homework should have unlimited attempts. And you have a couple options here. So there are some problems like, I think everything should be unlimited attempts, but if something is giving you like issues and it's not allowing you to do infinite attempts, at this point, I would just forget about it like I said, if you can make it 90, like that's not going to happen 10% of the time. Like if you make it to 90, you'll be fine. If you leave a problem or two out, it's going to be fine. I have another question here in the chat, but they typed out an integral. So hopefully I can actually get this correct. So one was the integral of x times the square root of 8x squared plus 48x plus 65. And another one is the square root x divided by the square root of -8 minus 4x squared minus 16x. And the problem is it's like choose the best trig substitution. Did I get those right? Okay. Yeah. So these will be kind of annoying to work out directly, especially I want to get to other questions. So I will just actually cheat a little bit. But the idea is you're going to complete the square here. Because to actually choose the right trig things, you would complete the square. So in the interest of time, I'll just let the computer complete the square for me, and then I can answer this. So right, so the first one is actually, if you complete the square, you would get 8 times x plus 3 all squared minus 7. Now, I'm assuming that you'd be able to get to that. In a test, I would give you nicer numbers. And for this one, if you complete the square, so what we're doing here is completing the square. That's something that you need to know how to do, because you not only need it for this, you need it for like hyperbolas and ellipses and all that stuff. So to complete the square for the second one, this one actually worked out to 8 minus 4 times x plus 2 squared. Right. So, okay. So if you're in this scenario, you need to do a trig sub. Remember, trig substitutions go based on the form x squared minus a squared, or x squared plus a squared, or a squared plus minus x squared minus a squared minus x squared, or x squared plus a squared. So you have to write it in that form. Having it in this form, the ax squared plus bx plus c is useless. So if you have to choose a trig sub based on that, what you would do is you would have to first complete the square. So then you'd complete the square and you'd get this. Now, once you get that, I would kind of rewrite this also. I would need the 8 to be a part of the thing. So it would be something like radical 8 times x plus 3 squared minus radical 7 squared dx. And so this looks like x squared minus a squared. And we know for that, the substitution is secant. Right, so this would be radical 8 times x plus 3 equals radical 7 secant theta. would be the correct substitution. For this one, again, you would realize that this is 8 minus, here I can think of this as 2 times x plus 2 all squared. And so I would think of this as a squared minus the x squared. And so the correct substitution would be x. For a squared minus x squared, it's going to be like a cosine. So it's going to be radical 8 cosine theta. And that would be the correct trig substitution. Notice that I have an equation here. It's this equals that. So it's not just x equals radical 7 secant. It's there's like a whole thing equals. So I don't know if they want you to write it as x equals something, in which case you just divide by the radical 8 and then subtract 3. But it's not just x equals, it's like a whole radical blah 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 equals. Yeah. So your generic x here is just whatever the variable part is. This entire thing in the square, the variable, that's the x in the general trig subformulas that I gave you. Okay, any other questions? Any more questions not related to the practice test? And yeah, Nadia, I see what you're saying, but I would, like I said, if at the end of the day, like you don't make the 90, then I would consider these problems. Like if you're sure you can get over 90 by ignoring them, then I would just ignore them. Like you'll see your score in the thing. And so that's something that we can deal with even this weekend. Like I wouldn't even worry about it right now before the test.
I have a question.
Yes.
So on this test, is there going to be like bonus with stuff that was covered after the same way there wasn't?
No, I don't think I put any of this, the bonus. I don't think I put any, no, the bonus is still the same on the same topics. So it's not anything that we've covered after.
Okay.
So the bonus would be, there was a point where I said, okay, the test is on everything above this. Yeah, so here you see test 2 material, the arrow pointing up.
Yeah.
Yeah, so you only need to know everything above that for the test, including for the bonus problems.
Okay, thank you.
So yeah, normally my bonus goes ahead, but it turns out like a lot of these other topics that I covered, in my mind, they're kind of optional to cover. You know, so it's like I'm not going to force you to actually know them. I'd rather actually test you on bonus for stuff that matters more. Like, I mean, sketching polar curves is cool and all, but like after Calc 2, you're never going to have to do this, like ever. Like it's just like a Calc 2 thing. So I feel like me asking you to do a bonus problem on something like this would be kind of like reinforcing something that you're never really going to use. I'd rather ask a bonus problem on more series problems because series are super important beyond Calc 2 and across multiple different disciplines. So yeah, I'm not going to ask you about areas or anything like that. So the test 2 material, including the bonus, is just everything that was above that arrow. And everything after test 1, everything above this arrow. Other questions? Okay, so like I said, you guys can email me. We'll also have time after class tomorrow to answer any questions. So for those of you who want to do the practice test, try to get it done by tomorrow's class, and so you can ask more questions. For those of you who have attempted the practice test, at this point, I'll hang around. You guys can ask me questions about the practice test. For anyone who has not done the practice test, I would say now is the time to actually step out. So have a good night. Go do the practice test. But for anyone who did it, which I think is like 3 or 4 people. So the 3 or 4 of you can hang around. And if you want to ask me anything about the practice test directly. Yeah, 4 people attempted the practice test. So if you guys want to hang around and ask me questions on the practice test specifically, I will do that. Everyone else, have a good night.
I have a few questions about the practice test.
Yeah, hold on.
Could you go over question number 9, where we have to approximate the integral from 0 to 1?
Wait, hold on.
Can you see the problem, or I can type it out if you need?
No, I'm actually just waiting on the other people. Yeah, I'm just waiting on those. The other people too. All right, no worries. You're welcome. Good night. Okay, all right, cool. So we're here. All right, very intimate gathering. So let's continue. So this is on practice test 2.
Yeah.
Okay, cool. What question?
Could you go over question 9, please?
Question 9. Okay, so Q9. That's the one to approximate the integral from 0 to 1 of 1 over 1 plus x to the 8.
Yes.
Right, so approximate using 2 fractions. So you have the answer choices there. The correct answer choice was 1 minus 1 over 9. Just for some foreshadowing. So the idea here is to, if you look at 0 to 1 of 1 over 1 plus x to the 8, you can look at this as 1 minus a minus x to the 8. This is actually a series because that reminds you of the series 1 over 1 minus x, you know, is just x to the n. But here it's like your x is replaced by minus x to the 8. So this just becomes the series of minus x to the 8 to the n. By the way, that absolutely converges, so you can actually switch the series and this integral. And this is by absolute convergence. So then I would do the power rule for this. So that's minus 1 to the n, add 1 to the power, divide by the new power between 0 and 1. Of course, when I plug in 0 for x, everything dies. So I just plug in 1 for x, and I have this. This is an alternating series. So the alternating series approximation there, well, I didn't even need to do that. It didn't ask me for a restriction. It just says approximated with 2 fractions. So I just evaluate 2 fractions from this. So this is approximated by plug in n equals 0, get the first term, plug in n equals 1, get the second term. If I plug in n equals 0, I get 1, minus plug in n equals 1, I get 8 plus 1. So it's 1 minus a ninth. So yeah, this is just using the series to approximate it.
Okay, thank you. I'm also just scrolling to see what other ones I had trouble with. For question 14, find all polar coordinates equivalent to the point r comma theta. It's question 14. Assume n is arbitrary. I didn't know what to do there. Also, there was 2 sets of coordinates.
Wait,
And I
question 14.
Yes.
So it's find all points equivalent to like r theta equals minus 10 pi over 3. So first I would actually sketch this. So if I go pi over 3, right, to go towards pi over 3 with that way, but I actually go backwards. So this is the point down here, minus 10 comma pi over 3. Now the thing is, you would actually get the same, if this is pi over 3, you'd actually get the same answer if you go around 2 pi, right? So if I start here and I go around again, I would get the same thing. So one set is just minus 10 pi over 3 plus any multiple of 2 pi. So that's one set. Another option is to first go here, which is on the green line, and then flip negative. So I could go, yeah, that's just directly 10. 10 in the direction of pi over 3, but I want it to actually flip to the positive. So I would go a positive distance 10. It's the other way. Where is it? So remember, there are always 2 sets, one with the r positive and one with the r negative. R positive means I'm measuring in the direction of the angle. So I want this angle here. So that is what I would measure. And this is going to be 4 pi over 3. So this would be 4 pi over 3 plus any multiple of 2 pi. And why it's 4 pi over 3, you just have to remember its reference angles. So here's 0, here's pi. Pi over 3 means you take pi, you divide into 3 equal sections. And then you would do the same for the bottom. And these will give you all the reference angles. So if you do this to get to here, Notice that how many pizza slices you count off? 1, 2, 3, 4 slices of pi over 3. So it's 4 pi's over 3. So this is 1 pi over 3. This is 2 pi over 3. This is 3 pi over 3. This is 4 pi over 3. This would be 5 pi over 3. This would be 6 pi over 3, which is 2 pi. So one of them, you want this angle and a positive radius. Another one, you want the pi over 3 and a negative radius. And that would give you all possible ones. So whatever option that was, the option that lists both of these together.
Okay, I get that now. Also, is there going to be any way to see the correct answers for the multiple choice? Because some of these questions, like I can go over the concept alone, but I just don't know which is the correct answer. Like I don't see the correct answers, or what I got wrong.
So the answers get revealed tomorrow at 2.
Okay, and then the
But
exam
if-
opens at 3.
And the exam opens at 3, and then you have until 9 p.m. the following day. So the
Okay.
thing is, I don't know if I can actually. Yeah, so what I can do is I could send you the answers now.
Okay. I don't mean to be like
guess-
pushy
I
about
guess-
it. I've just been stressing out about this exam because it's like the last one, and I'm so excited because like Calc 2 is gonna be over. Like it's a great subject, but like, yeah.
Yeah, it's intense in the summer. So who else is here? I think Molly actually gave you already.
So I would appreciate it if you could send it to me, and then I could just review in the morning tomorrow before the exam.
Yeah, so I just sent it to the both of you. So you can check those. It's set to send to the rest of the class tomorrow as well. So you guys might get a double email of the answers. But since you're here tonight, I just sent it to both of you. All right, good night, Nadia. Maxim, you have any questions?
Yeah, just a really quick conceptual one. Other than that, I was just here to benefit from other answers. But for a question like 10, where it has partial sums and it has the series, S sub n would be the sum of all of the A sub n's up to that point, right?
Yes,
Okay, so in this case, finding A sub 5 is just S sub 5 minus S sub 4.
correct. Yeah,
Okay.
so yeah, so S sub n is always the sum of all the A's up to, so whether you start at 1 or 0 depends on the series. So you'd actually look at the series. So this, it's talking about a series starting from n equals 1, right? Of an. So it starts at A1, but then it will count up the first n of these. And you're told that S sub n, you can write it as 4 plus 2 over n. And you're asked, what is A5? Well, just notice that S5 minus S4, that's going to be like A5 plus A4 plus A3 plus A2 plus A1 minus A4 plus A3 plus A2 plus A1. So all of these guys would cancel each other out, leaving you with only A5. And so now you just plug in this formula. S5 would be 4 plus 2/5 minus S4 would be 4 plus 2 over 4. And I think the answer is 110. Yeah, so Sn counts all terms, the first n terms added together. So So there is a scenario in which Sn is going to be A0, A1, all the way up to An minus 1, or it's going to be A1 all the way up to An, depending on if you're doing the series starting at 0 or you're doing the series starting at 1. But it's always the sum of the first n terms.
Okay.
Yeah.
And for representing a function as a power series, we have the basic cases, but other than
Yeah.
that,
Yeah, it's going to be in the table where, so there are two cases that you'd have to worry about. So one is directly from the table with the Maclaurin series. Yeah, so one is directly from this. So anything that can be written as these, so an exponential or a cosine or a sine, or anything that looks like a fraction with two terms in the denominator where one is a constant and one is a function. So anything of that form. So you can have like a 1 over a constant plus a function, or you can have like e to some function, or you can, and even like a polynomial times that, like an x times that can work. You can just multiply in the x, or you have sine of some function, or you have cosine of some function. So that's one scenario. If you have any of these, you just, first of all, you would factor out the a, and then this would be 1 minus f over a, right? And then this you look at as 1 over, this would be like the sum of f over a to the n, right? As a power series. And these guys will just look like, you know, this would look like x times the series of this to the n over n factorial, right? So it's all based on this table. So that's one scenario. You can actually just directly plug into these. The other scenario is where you're just like one step away from these things via like differentiation or integration. So that would be like if I have something like ln of a 1 plus x, I realize that that's just like the integral of 1 over 1 plus x. And I can write this as a series and integrate it so I can figure out that as a series. Yeah, so you're either going to be something directly in this table, or you're going to be the integral derivative of something in the table. The nice thing is, with these guys, the integrals or derivative is going to be the same kind of function, right? The integral derivative of cosine is going to be a sine, and vice versa for the other one. The only one you'd have to worry about is like this guy is going to be, if you're one step away from him, you could be like an ln, or you can be like 1 over a sum squared, right? And you kind of recognize it like that. So you're either going to be like these guys in the table, or you're going to be like one step away from these guys in the table. So those are the two main scenarios. And yeah.
Okay, thank you. I think that does it for me, so good night.
All right. Good night. Good night, Molly. And yeah, it's just me here, but I guess I'll see you guys in the next one. Ciao.